Let's keep going. All right, let's keep going. Now you're transporting your fats that you have eaten in your diet. You take into different tissues, right? They need to be digested, right? Or you starving yourself. Now the opposite direction occur. Fats get mobilized from your fat cells and get taken to a tissue for energy purpose. By any case, fat is when it's taken to different tissues, especially in the muscle tissues, they have to be degraded. And this degradation we're going to talk about, called the beta oxidation. Okay. At that point, the end product is acetyl-CoA that you heard about a lot. This is one way you can get a lot of acetyl-CoA, which is basically a supply for the Krebs cycle for energy purpose. Is that clear? All right, so let's keep going. So that's the big picture here, okay? Now you're starving yourself for some reason, or you want to lose weight, now, at that point, your blood glucose starts shooting down. Now you get nervous. Epinephrine level goes up. Glucagon goes up. Insulin goes down, right? Now the fatty acids now get released because the fats now heard the news that you are starving because your blood glucose is coming down to release fat. Now that you have storage for raining days, now the raining day is here. Okay, so the fat get mobilized from your tissues, and now taken from your fat cell and get taken to different tissues. Then they get degraded. Okay, as you see here, the fat from your triacylglycerol from your fat storage now feed into the synthesis of acetyl-CoA, and acetyl-CoA get to the Krebs cycle. Okay, or it could be you had just eaten very well. And then the fat that is in your diet, now taking your chylomicron, go to your muscle cell. The muscle cell, okay, you don't need to send any more fat from fat storage. You don't need to use that much glucose, a little bit, but I will utilize the fat that comes from the diet for energy purpose, okay? So at that point, the fatty acids that are coming from your diet can also get to the Krebs cycle, break down to acetyl and get to the Krebs cycle, okay? So keep in mind, it doesn't have to come only from your fat storage, but it can also come from your diet. Is that clear? Okay. Now the mobilization. So we have already spoken about the lipoproteins a lot. So we're gonna focus on when you're starving and how fat get mobilized and get degraded. Okay. Now this is a process when you, as I said, you're starving, the fat is needed to be mobilized from your fat cells. It's nice and full here after you spend months of eating well. Now you're starving, the triacylglycerol now get released, you have a free fatty acid, get transported to different tissues for utilization, okay? One question to you, how the free fatty acid is transported in the blood? It's bound to what? Free fatty acid. Now it's not ester, it's a free fatty acid from the fat cell. The HDL, the chylomicron? No. That's a new transformer called the albumin. All right? So keep that in mind. When you have your fat storage, now, fat from your fat storage, all the lipoproteins that I mentioned is the transfer from your diet or from your liver. But what I'm saying now, you're starving yourself, the fat's getting mobilized from your fat storage, those big guys full of, so the free fatty acids, it's not the triacylglycerol, it's the free fatty acid. So fat get clipped off and released in the blood and taken to your tissues. That free fatties get transported by albumin. Keep that in mind. And that's important. We're going to talk about that now. I'll just anticipate that. So muscle will utilize the fatty acid for energy because you're starving. But it turns out in the liver, the fat can be broken down to acetyl-CoA. And the acetyl-CoA can also be utilized to synthesize ketone body. And that occurs in the liver, and we're going to talk about that too. It turns out the brain cannot utilize fat, okay? So the brain will rely either on the glucose or the ketone body that is synthesized by the liver. So this is where when you're in a starvation condition, the fact that the brain cannot utilize the fatty acid, and the brain will rely on the glucose at that point. And you're starving, and your blood glucose is dropping, so your brain will start utilizing other source of energy, so the blood glucose will not go down too fast. At that point, the ketone body is synthesized by the liver and shipped it to everybody else, including your brain. Is that clear? We're going to talk about it a little more as we go, okay? But so far, this is just to give you a little bit of information on it. All right. So now when the fat is degraded, the free fatty acid that I mentioned is taken by the albumin, transported by the albumin. The glycerol backbone is shipped where? I said that earlier. To your liver for gluconeogenesis, especially when you're starving, so it's going to be utilized mostly in the gluconeogenesis. Is that clear? Good. All right. Now here is the signal. You're starving, you're getting nervous, insulin level drop, right? And glucagon level goes up. So epinephrine level is up. And those epinephrine and glucagon can bind to their specific receptor, and you have a signal that is sent inside. You went over signal transaction already, right? You know PKA, protein kinase A? So cyclic AMP will activate the protein kinase A. You take 4 cyclic AMP to activate one protein kinase A. That protein kinase A then become active and get into the adipocyte, not the adipocyte, the lipid droplet. And inside those lipid droplets, it cleaves all the fatty acids off. You see they have a triacyl glycerol. So the fatty acids are now cleaved off, okay? Those free fatty acids now are released in the blood. And you see now what I said earlier. The fatty acids are transported by what? Serum albumin. So if you are low in serum albumin, can you transport your fatty acid? And so keep that in mind, okay? And I think it's the disorder associated with that, if your liver cannot produce enough serum albumin, okay? So deficiency on your serum albumin can lead to muscle weakness, cramps, and so forth, because you've now been able to transport the fatty acid inside your tissues to be utilized in a beta oxidation, okay? So far, just keep in mind what we said here. The free fatty acid that is released from your fat storage now transported in the blood to what's called, by what's called the serum albumin. And then once you reach the respective tissues now, the fatty acids is released and get inside the cell by a fatty acid transport proteins, which is located at the cell surface. Is that clear? Now, once the fatty acid is inside the cell, so the fatty acid get activated and go to what's called the beta oxidation. Okay? And it's that beta oxidation we're going to go over in detail. Okay? So now, at the end of the day, what you're getting, a lot of acetyl-CoA, and the acetyl-CoA go through the Krebs cycle. I know you know that already. And the Krebs cycle, you generate a lot of NADHs, and the NADH you oxidize in electron transport chain, you generate a lot of ATP, right? So now, you generate a lot of ATP, okay, in the myocyte. Is everything clear on this one before I move on? But this is important. Okay, all right. So now that we have transported fatty acid to tissues, we're going to talk about the metabolism. All right. There's a lot of moving part in there, but we're going to take it one at a time and make it clear, okay? So now it turns out, if you recall these proteins, when fatty acid is transported to the bloodstream to tissues, right? And it gets transported inside the cell by these proteins, okay? These are the transporter proteins, okay? The FAT, the CD36, and so forth. So once they get in, what happened, the fatty acid is attached now to OCoA, okay? So now it turns out one thing you have to remember in this slide, short-chain fatty acids will go straight across the membrane. They don't require a transport mechanism, okay? And medium chains as well do not require transport. And that's important, right? So short chain and medium chain, there are chains that have 2 to 4, 6 to 12 carbons. They can diffuse straight up across the membrane and get attached to a CoA. But the long chain fatty acids, C14 to C20, they're the one who require the transport mechanism across the membrane. Is that clear? Good. Now, once they get it inside, so the free fatty acid that has to be attached to a CoA, and that reaction is catalyzed by an enzyme called acyl-CoA synthase enzyme. So basically, the fatty acid is now esterified to that molecule, the CoA. Okay? Now you have synthesized what's called acetyl-CoA, the acyl-CoA. Not acetyl-CoA, but acyl-CoA. Acyl means fatty acid. Okay? So acyl-CoA, so you have your long-chain fatty acid attached to a CoA. So now this molecule cannot go across the mitochondria. It has to be transported. Okay? If it's a long one, right? We're going to talk about that. So that's the action of the activity of the acyl-CoA synthase, fatty acid attached CoA. And it requires ATP, so it's an energy requiring reaction. Now, entry to mitochondria. So now that your fatty acids are taken in your cell, they have to go through the mitochondria. Again, the same rule applies. Short chain and medium chain, they're happy, they go straight across the mitochondrial membrane. Okay? But the long chain fatty acid that is esterified in the cytosol now has to be transported across the mitochondria. Now, that transport mechanism is very, very important. Okay? Especially these enzymes, this protein called carnitine acyltransferase 1. Okay? Some call it fat, some call it carnitine acyl or fatty acyl transfer protein. And so you have different, but as far as we're concerned, carnitine acyl palmitoyl transfer protein, okay, or CAT, carnitine acyl transfer protein, I'm sorry. Let me back up. In some books, you see both names, so you call CAT, carnitine acyl transferase protein, transferase protein, or carnitine palmitoyl transfer protein. Is that clear? Okay. So some books entertain, but I want you to know both names, okay? So it is a transfer. What this enzyme does is took the fatty acid from this and attach it to the carnitine. Instead of being in the CoA, it take it from the CoA and attach it to carnitine. The reason for the CoA cannot go across the mitochondrial membrane. CoA cannot go. There is a pool of CoA inside the mitochondria, there is a pool outside the mitochondria. And the two pools do not mix. So it turns out when the fatty acid attached is now transferred from the CoA to carnitine and forming the fatty acid carnitine, that complex is translocated in the mitochondria, in the mitochondrial matrix. But remember, the formation of this is in the intermembrane space. The carnitine palmitoyl transferase protein, 1 protein is at the outer membrane. So here, the inner membrane is the one that is really not permeable to any molecule. Everything is controlled before it gets in, okay? So now once that occurs, you have a carnitine acid a fatty acid carnitine formation. The fatty acid carnitine is now translocated in the mitochondria matrix. Now there is a second transferase enzyme called carnitine palmitoyl transferase 2, okay, or carnitine acyltransferase 2. So one is outside to the outer membrane, but the two now is inside in the membrane that take now the carnitine fatty acid carnitine and transfer now to CoA. You remember I said there is a pool of CoA in the mitochondria and a pool outside the mitochondria. The two pools do not mix. Is that clear? So basically, everything these mechanisms have done is to take a fatty acid here, modify fatty acid CoA here, modify and take it back in the mitochondria and originate back in the mitochondria. Is that clear? So all this transfer to carnitine and taken back is to basically carry the fatty acid inside. Once you occur, the fatty acid is removed from the carnitine and get back and now attached to a CoA. And the carnitine go back outside and accept a new molecules, fatty acid molecule, and bring it back in. Is that clear? So carnitine is a transfer mechanism. All right, we're going to talk about this enzyme a little more, okay? I know it sounds complex, but it's not that complex, okay? All right, so once that occurs, so you have your palmitoid transfer. But now one thing I want to bring it to your attention, if I can. One thing I want to bring it to your attention is the carnitine palmitoid transferase 1. This guy is sensitive to malonyl-CoA. Okay, it's regulated by malonyl-CoA, and that is important. Keep that in mind. Because that's a regulatory point. So if the fatty acid has to be degraded, here, this is another one. I put it there. I know this may look a little, it's comprehensive, but less clear as you will see here. So if you didn't understand the transport mechanism earlier, I can explain from here. Okay, so here, if you look at it here, this is a matrix, and this is the intermembrane space, right? Now, your fatty acid that I have mentioned earlier that is here is right there. The fatty acid CoA here, as you see, is transferred to carnitine. So the carnitine is outside. The two are combined now by the enzyme, the transferase 1. So now you have a fatty acid carnitine. Is that clear? Now this complex now is taken inside by the translocase. Now once they get in, your fatty acid carnitine that you have here, once you get in, the fatty acid is now passed to the CoA. You see the free CoA here? So once that occurs, you have a fatty acid CoA now. And the carnitine that is transporting it go back and it's taken outside of the matrix and accept a new fatty acid. Does that make it clearer? Simpler? So you have two possibilities. I put this like I said, this looks a little complex, but this makes it a little easier on you, okay? One thing I want you to understand, you have a carnitine transferase 1, you have a carnitine transferase 2. The carnitine transferase 1 is the one that is sensitive to malonyl-CoA, okay? And there is a reason for that. Malonyl-CoA is the building block for fatty acid synthesis. And you will see that 2 days from now. Now, when you want to synthesize fatty acid, then you synthesize a lot of malonyl-CoA. So you do not want to break down fatty acid while you're ready to synthesize one. Okay? So once the malonyl-CoA level goes up, it's an indicator that you want to synthesize fat. So you do not want to synthesize fat and break it down again. Because the breakdown of the fatty acid occurs where? Fatty acid degradation takes place where? Inside the cytosol or mitochondria? Mitochondria. Keep that in mind. And usually, glycolysis takes place where? In cytosol, right? So now these two enzymes, the transferase 1 and transferase 2, one is outside and one is inside, are very, very important. They have to be healthy in order for the fat transfer to occur and get degraded in the mitochondria. Everything I said just now is to transfer fatty acid from outside in the cytosol all the way inside the matrix to be degraded. Is the transfer mechanism clear? All right, good. Yeah, inside the matrix, that's where the fatty acid breakdown occurs. Okay. All right. Because the reason I have this one also, keep in mind, here is you don't see it clearly, but this is carnitine palmitoid transferase 2, and this is 1. Because it's not well written, but here it's well written, so you can see it both. So the malonyl-CoA, as I mentioned, malonyl-CoA inhibits the carnitine palmitoid transferase 1. And this malonyl-CoA is synthesized by the action of this enzyme, acetyl-CoA carboxylase. And again, we're going to talk about this a little more in fatty acid synthesis. But for now, this is the only thing I want you to know about the malonyl-CoA. It inhibits carnitine transferase 1. Okay? Carnitine acid transferase 1. Is this clear? All right. All right, so now we have your fatty acid transferred from outside to inside the matrix, right? It's a lot of moving part here? But it's very simple. Once you start going over, it's very simple, okay? So now we have our fatty acid inside the matrix getting ready to be degraded. And now we're going to go to the real beta oxidation. Okay. Now I'm going to give you some of the feature of it. So beta oxidation basically is a major pathway of fatty acid breakdown, I always said. It occurs in the matrix, not outside of the inside the mitochondria, in the matrix. Okay, it takes place in different tissues. So all the tissues that utilize fatty acids, which include everybody almost, except your brain and red blood cells, right? Because red blood cells, they do not have mitochondria. Okay? So they tend to rely on but the brain can also utilize ketone body. We're going to talk about that. But the red blood cells definitely have to have glucose around in order to survive. All right, so this is your beta oxidation that has been so much mentioned. So that's the steps. And we're going to go over slowly, okay? It's not that complicated, but it can be a little intimidating sometimes. So it has this, the first step. Now this is your fatty acid that is coming. In this case, we have palmitoyl-CoA, which a palmitoyl is a 16-carbon molecule, fully saturated, okay? Now, there is the first steps where you create it. And then again, one thing I mentioned to you during fatty acid chemistry is alpha carbon and a beta carbon. I mentioned carbon number 2 is the alpha carbon, and carbon number 3 is the beta carbon. So this is carbon number 1, okay? So in fact, what happened is that you are creating a double bond between these two guys, okay? The initial step is to remove 2 hydrogens, okay? So it's called the acyl catalyzed by enzyme called acyl-CoA dehydrogenase. So basically, you're taking hydrogens away, creating a double bond, okay, between the alpha and the beta carbon. And the hydrogen that you're removing from here and there, you are give down to FAD. The FAD now is converted to FADH, okay? What happened to the FADH? You have to connect everything, the dot. What is the fate of the FADH? Electron transport chain. Okay, good. So you generated FADH that can go to the electron transport chain. Now, what happened, once the double bond is formed, now the water come in, so you're creating the OH group by splitting the water. The hydrogen is attached to this carbon, so you have a CH2, and the OH now is attached to this carbon. Now you have a hydroxy group here, okay? So that reaction is catalyzed by what's called enol-CoA hydratase. Basically, you take water, cleave it, and put it across the double bond. So that will create an OH group here. Now, the next step, what you do is to create a ketone group, basically on this beta carbon. So in order to do that, you remove the hydrogens, both hydrogens on this molecule, and that reaction is catalyzed by enzyme called beta-hydroxyacyl dehydrogenase. Basically, it's taking the hydrogen from here and there, and then attach it to NAD+. Now you have an NADH form, okay? So you have your ketone group now that is generated. Now the last step, there is an enzyme called the thiolase, or acyl-CoA acyltransferase. So basically, it takes the fluorine-CoA and attach it to this end here. Now, when that occurs, these two carbon molecules attached to CoA is now free. And this is your acetyl-CoA. Is that clear? So basically, it is reduction basically removal of the hydrogen and attachment of water, oxidize that, and now cleave it off, okay? So basically, it is a series of steps, the dehydrogenation, and then hydration, and the cleavage. Now you have your acetyl-CoA. Is the steps clear? Now, what you have to remember, you have an NADH and you have an FADH. And this one, how many carbon did we cut off so far? 2, right? Now, how many carbon is the palmitate I said earlier? 16. Now, if you want to clip the whole 16, what would you do? How many times you have to do this? 8 times? How many times? 7, right? So you have to do this 7 times, right? So when you do this 7 times, how many acetyl-CoA would you generate? 16 carbon divided 7 times. Remember, the last one will come off from the last 2 come off from the other. You take the last 4, you divide it into 2, and you have an acetyl-CoA, another acetyl-CoA. So you divide it 7 times, it generates 8 acetyl-CoA. Okay? So you see, you do that 7 times, and you have all those 8 acetyl-CoA, okay? So what's the fate of the acetyl-CoA? It's right there. You go to acetyl-CoA. You have to link things together. That's the only way you can memorize biochemistry. You don't want to just purely memorize. You have to understand things and connect the dots. It make it easier for remember. So the acetyl-CoA is utilized in the Krebs cycle. Remember that? So you go through the Krebs cycle and you generate even more NADHs. So you generate a lot of FADHs here and NADHs here. So how many FADH are you producing from per palantate degradation? Complete degradation, at least for a bigger oxidation in this process. How many FADH are you producing? Huh? 7, just say it. It's okay to be wrong, just say it. It's 7, because you cut it 7 times, so you created 7 FADH. How many NADHs? How many water do you use? Okay. And it generates 8 acetyl-CoA. So all those acetyl-CoA could go to the Krebs cycle. NADHs and FADHs can go through the electron transport chain and ATP. Now, you're going to generate a lot of ATP from the Krebs cycle, okay? But also the acetyl-CoA can also be utilized to synthesize ketone body. You remember this? So in your liver cells, once this occurs, and you have a lot of acetyl-CoA, not only some can be utilized for Krebs cycle, but some can be utilized for the synthesis of ketone body. And once the ketone bodies are synthesized by the liver, you ship it to different tissues, especially on the brain, so brain can utilize those for energy. Because you remember you're in a starvation condition. Is this clear? All right. Now, I mentioned this in the gluconeogenesis, if you recall. Now, if you have odd number of carbon molecule, fatty acids, okay? You're cleaving by 2 carbons and 2 carbons. At the end, how many carbons you're gonna have? Huh? 3 carbon, right? If it's an even number, then you're gonna cleave, the last 2 will be acetyl-CoA. Now, if you have uneven number, odd number of carbons, then you're gonna end up with a 3 carbon molecule. You cannot cut a single carbon off. So you're gonna end up with a 3 carbon molecule, okay? And that's what is called the propionyl-CoA, okay? So when you clip it all, you're gonna generate a lot of propionyl-CoA, okay? So the propionyl-CoA also has to be utilized. Can propionyl-CoA go directly to the Krebs cycle? Did you ever heard of propionyl-CoA getting the Krebs cycle? So it has to be modified, right? And that's what we're gonna talk about, okay? So the propionyl-CoA has the 3 carbon molecules and is attached to CoA just like an acetyl-CoA. Now it's converted to an intermediate molecule, methyl-malonyl-CoA. Now by the action of this enzyme called propionyl-CoA carboxylase, what this enzyme does is to take a CO2. Again, anytime you see bicarbonates like this, it's just a CO2 donor, okay? Beside the pH stuff. But here, sometimes when you see bicarbonates, it's given in a reaction like this, is to give the CO2. Okay, so basically it is a dissolved CO2. Is that clear? So the propionyl-CoA, what it does is to attach the CO2 to this propionyl-CoA. Now you have what's called the methyl-malonyl-CoA, but it is put at the position here too. So now the methyl-malonyl-CoA epimerase now, what it does, it creates an epimer, basically move it out, getting ready for a further modification. Now you go from the D to the L-methyl-malonyl-CoA, okay? Catalyzed by this methyl-malonyl epimerase. Now once you have that, now there is another enzyme that takes this carboxyl group and put in the back of the molecule. now you have your succinyl-CoA. Okay? This reaction, carboxylation, okay, one thing you have to remember as a general rule, anytime you have a carboxylation, usually biotin is involved. Okay? Now, if you have decarboxylation, usually TTP is involved, thymine pyrophosphate. Okay? So keep that in mind. Now, in the last reaction here, you have vitamin B12 is involved. This is one of the two reactions where you see vitamin B12. It's very, very important because in a sense, you remove a covalent linkage and attach it to another. So B12 is involved in this process, okay? So now it turns out when you have a B12 deficiency, okay, you will not be able to complete the succinyl-CoA synthesis. Now, all of you know succinyl-CoA now, right? And the reference to TCA, it's part of the TCA, right? So now this molecule can go through the, so if I ask you a question, the propionyl-CoA get to TCA by what form? Intermediate. It will be succinyl-CoA, right? And what else the vitamins require? B12 and biotin, right? And again, carboxylation. Anytime you have carboxylation, you have a biotin involved in that process, okay? Now, it turns out when that occurs and you deficient vitamins B12 and you have issues associated, especially megaloblastic anemia, okay? But you also have methylmalonyl acid formation, and that can be diverse in the urine, and they can test that to see if you have a B12 deficiency, because if it is the case, you will see it is accumulation in the urine, okay? So as you see here, the methylmalonyl-CoA is because they could not go beyond this step if the B12 is deficient, okay? So this is tested in the urine. Is this clear? All right. So this is where your succinyl-CoA get into the Krebs cycle after you synthesize, but it will not generate enough ATP. I'm not asking you to memorize this. I just want you to know that succinyl-CoA get into the Krebs cycle here, while acetyl-CoA goes. So it get in halfway, so it will not generate enough ATP for that matter. Okay. All right. So we went over very much over the beta oxidation. Again, one of the portions you have to remember the beta oxidation, especially the first reaction, the dehydrogenase, is very important. And we're going to talk about it a little more as we go. I know sometimes too many steps for you guys. You know, try to be a biochemist. We give you the entire casket and then point out some key area that you need to remember. Okay, so regulation. All right. For fatty acid to be degraded, what has to happen? If it's in the cytosol, it has to be transported where? To the matrix, right? And what is the rate determining step of the transport mechanism? A key enzyme that is very important in the transport. Carnitine palmitoyl transferase enzyme, also known as a carnitine acyl transferase enzyme. As I said, this enzyme is regulated, okay? Now, it's regulated by malonyl-CoA. So malonyl-CoA level goes up and shut down, so you will not be able to take your fatty acids inside or break down, right? And that goes up when acetyl-CoA is converted to malonyl-CoA, which is catalyzed by this enzyme, okay? Acetyl-CoA carboxylase enzyme. This enzyme requires which vitamins? Malonyl-CoA synthesis, acetyl-CoA converted to malonyl-CoA. Basically, it is a carboxylase. It requires what vitamin? Biotin, right. So this is the enzyme here. So when this enzyme is activated, malonyl-CoA is forms and they can shut down. So what condition this enzyme will be activated? Do you want to break down, when it's active, do you want to break down fatty acid? If it's activated, malonyl-CoA is up. No, exactly. All right. So, and now you get, in order for, if you want the fatty acid to go inside, what would you do with this enzyme? You say that again? If you want malonyl-CoA level to go down, what would you do with this enzyme? Huh? Yeah, you shut it down, right? And that shut down if you get phosphorylated. Because phosphorylated by this enzyme, that enzyme is activated when, what AMP really means? In low energy state, right? So when you're in a low energy state, do you want to synthesize fat or you want to break it down? When I break it down, so AMP is up, activate this enzyme, phosphorylate this guy, and shut him off. So fatty acid can be taken inside for breakdown. Does that make sense? Good. All right. So the other way, again, it will activate this enzyme in case you have a lot of energies around. Activate this. So you have your low energy around. These guys, what this enzyme does is to shut down malonyl-CoA level. Basically, it converts malonyl-CoA to acetyl-CoA, so the malonyl-CoA level can even further go down. So if you're low in energy, AMP is up, this kinase will phosphorylate this enzyme and activate him in order to even further decrease the malonyl-CoA level. Is that clear? So not only you blocking the synthesis, but those that are already there, you're trying to hydrolyze them. Is that clear? So that's how when you're in low energy state, it stimulates fatty acid breakdown. Now, the descriptions are here, okay? What I say from here, but if you start getting confused, you just read from here. All right? All right. Interrogate. This is important. Now we're trying to do a little more integration because we are discussing a lot of mechanisms that are interconnected, but we have to sometimes explain the interaction between fatty acid and beta oxidation. Now, it turns out when you start breaking down fatty acid, you say, at what condition? Are you in a high energy state or low energy state? Energy state. So you're fasting, for instance. If you're fasting, you start breaking down fatty acid. Fatty acid start breaking down. What will you do with the enzymes such as the pyruvate dehydrogenase at that point? You generate a lot of acetyl-CoA. Look at what acetyl-CoA has on pyruvate dehydrogenase. Nobody see it? The pyruvate dehydrogenase, it breaks down, you already have, synthesized, pyruvate dehydrogenase generated acetyl-CoA. If you already have a lot of acetyl-CoA, do you want to make more acetyl-CoA? Good. So now, you starvation condition. What happened to your blood glucose level? Down, right? And what do you want to do with your blood glucose level? You want to rise it up by doing what? Gluconeogenesis. Great. So the fatty acetyl-CoA will shut down pyruvate dehydrogenase. It will stimulate pyruvate carboxylase enzyme. You remember that enzyme? In order to gear up gluconeogenesis. So not only you are giving yourself energy through acetyl-CoA, but you're also gearing the cascade to a gluconeogenesis to maintain your blood glucose for your brain and your erythrocyte. Is that clear? Good. Now, when you shut down your fatty acid synthesis, what happened? For some reason, you shut down your fatty acid synthesis. What will be the impact on pyruvate dehydrogenase? That negative pressure is down, goes away, right? So how about the gluconeogenesis? The gluconeogenesis go down, right? Because you're shutting down the acetyl-CoA level that is needed in order to stimulating the carboxylase. Acetyl-CoA stimulate carboxylase to stimulate pyruvate carboxylase to stimulate gluconeogenesis, but shut down pyruvate dehydrogenase in order to shut down the synthesis acetyl-CoA from pyruvate. You remember that, right? In the gluconeogenesis, look at the gluconeogenesis. So this is an interconnection for you to see really, the two systems are connected. Okay, this is Basically, it's a switching off on and off thing. So when the fatty acids level is degradation level is high, so you would let's go back a little bit. When it's high, so you have acetyl-CoA, you already have enough energy, for your muscle. You want to synthesize the glucose from pyruvate. So now, if you are low on it, so you want to shut it down by the acetyl-CoA is not there, then the pyruvate dehydrogenase level is activity goes up, and then the pyruvate can go, which means you're in a high energy state. Is that clear? Is that clear? All right. So you have your whole clinical correlations. So a patient with deficiency in fatty acid oxidation, and this is important, especially, and we're going to talk about it a little more next year in your cardiac cells. So basically, it turns out when the failing heart, the heart is failing, for some reason lose the capacity of utilizing fat for energy. Your heart usually uses a lot of fatty acid for energy because it's always pumping. It needs a lot of energy. So now, if you cannot break down your fatty acid, what happened to your heart? What do we depend on energy from? Where the energy will come from? Somebody said it? Now, it depends on the glucose. So failing heart switch from fat utilization to glucose utilization, okay? So keep that in mind, okay? And that's important. So when the liver are failing, for some reason, the liver lose the capacity of utilizing fatty acids. So at that point, then it will rely mainly on the glycolysis for energy. So that's what you have to take on, okay? And the gluconeogenesis impairment. So it's a lot of issues associated. So genetic deficiency, so fatty acid degradation. So carnitine, as you know, carnitine is a transport mechanism, right? So if you're deficient in carnitine, then that will lead to deficiency in the fatty acid utilization, okay? So if that occurs, your liver can produce some carnitine, but for some reason, sometimes you can deplete it, and that can lead to issue, but you can easily take supplements in order to compensate for the loss. So it can be secondary to other issues. If you have defective fatty acid breakdown, so you have accumulation of carnitine molecule that can be excreted, so that way you can lose a lot of carnitine to that mechanism. Then you become low in the carnitine. Again, you take a carnitine for supplement. If you go to Walmart, you see those things, bottles, carnitine, that you can take as a supplement. It's not a vitamin because your body can produce it, so it's not crucial in sense that your body can produce it, but you can take it as a supplement. Is that clear? Some drugs also, if you are on some drugs, the seizure drugs, for instance, can also impair the absorption of carnitine. That can also be deficient. Now, the deficiency of the transferase, everybody should know this by now. If you have a mutation that for some reason your transferase is deficient, then that can lead to a significant problem because those long-chain fatty acids, why not short-chain fatty acid and medium chain? They don't require exactly. Okay. So, and your gluconeogenesis is impaired. Why? During fasting. Why? Again, make the connection. You will not synthesize enough acetyl-CoA to stimulate gluconeogenesis. So gluconeogenesis, so you can quickly run out of glucose if you're not synthesizing a new one, if you're in a starvation condition. Does that make sense? If you're not breaking down your fatty acid, so you're not synthesizing a lot of acetyl-CoA to catalyze, stimulate the reaction catalyzed by the pyruvate carboxylase for gluconeogenesis to go, because you need acetyl-CoA to stimulate gluconeogenesis. If you're not break down fatty acids, so you will not be able to stimulate that reaction. Is that clear? But it occurs mostly when hypoglycemia occurs when you're in a starvation condition. If you're eating, you're fine. Okay? The transfer to also lead to disorders affecting liver and cardiac cells and muscle cells and so forth. Okay? So for treatment, you have to avoid fasting. Somebody who has deficient in any of these, you have to avoid fasting, right? Because, as long as you eat it properly, you don't have any issue. Now, when you start relying on your gluconeogenesis, and the energy from your fat, that's when you start relying on having a problem. Okay. Now, some drugs such as the sulfonylurea drugs can also have impact on the cognitive transferase one. So keep that in mind. So somebody is on those drugs, you can inactivate this enzyme. So the person becomes lethargic because they're not going to be able to take fatty acid inside and break them down. Is that clear? This type of drug, sulfonylurea drugs, and some of them are the tolbutamine and the glubutyric drugs. So they will shut down the transferase, and the person will not be able to efficiently take fatty acid inside to break them down. Okay? And again, if you don't break down fatty acid, you have to rely on the glucose, the tendency to go to hypoglycemia, or the person will be lethargic. Now, remember I was saying the very step of beta oxidation, the step that is catalyzed by acyl-CoA dehydrogenase enzyme. That's the very first step of the beta oxidation, if you recall. The step, what molecule are you forming here? FADH, right? So now there are, depending on the size of the chain, okay, there are different isoenzymes that catalyze depending on the size of the chain, okay? And sometimes you can have a deficiency in these enzymes, and that can lead to significant issues. It affects, about 115,000 patients, and many of those are asymptomatic. The rest of them, develop a symptom that are listed here. Again, anytime you cannot break down fatty acids, you tend to be prone to hypoglycemia because acetyl-CoA now been generated. You cannot catalyze gluconeogenesis. No ketone body, because ketone bodies are needed for the synthesis for energy for brains and so forth, and they are synthesized from acetyl-CoA, and so forth. So the worst one is this guy, the medium chain deficiency, which is the most common one. So keep that in mind. I think I have a few things on that on a few slides. Now, ketogenesis, on the other hand, and everybody knows ketone bodies by now, right? Ketone bodies. So basically, when you're starving or uncontrolled diabetes type 1, so fatty acid mobilization occurs big time. So now the 3-fatty acid is utilized by the liver to synthesize ketone body. And we're going to talk about the ketone body themselves, but for now, just to give you a general pathway. So these are the two major ones, the beta-hydroxybutyrate and acetoacetate. And you also have an acetone, but that one is a volatile. We're going to talk about that. Okay? So ketone body is a major source of energy for brains and the muscle tissues and so forth. But liver itself doesn't use the ketone body. It utilizes the fatty acids, okay? And renal cortex. But now this is the synthesis. Again, what I want you to know, there are enzymes, this is the reactions. You have 3 acetyl-CoA, 1, 2, and another one here. So here you are synthesizing acetyl-CoA, basically attaching 2 fatty acids by the enzyme called the thiolase. Now you have a HMG-CoA synthase that catalyzes the formation of HMG-CoA from acetyl-CoA. Now, once that occurs, you have a lyase. Now you added 3 acetyl-CoA, you are removing 1 here. Now you end up with what's called the acetoacetate. And that acetoacetate now can spontaneously become clipped off. The CO2 can clipped off, and you have acetone. Okay? And the acetone is very much volatile. Now, somebody who is a diabetic type 1, or if you starve yourself, remember, if you are trying to lose weight and you starve yourself, 2-3 days later, you start having that fruity smell in your breath, it's because of the acetone. Because your fatty acid is breaking down, and you generate a lot of ketone body, and your body, since this is volatile, it starts coming out of your breath. Okay, and that's why people smell, especially when somebody is on type 1 diabetes and that is now controlled. Fatty acid mobilization is high because insulin is low, and that can lead to this ketone smell in their breath. Keep that in mind because they like to ask people those questions in the diabetic patients, the fruity smell on their breaths and so forth because of the acetone, okay? So these ketone bodies are acid, so they can cause decrease on the pH on your blood, right? And we're going to talk about that. But basically, these are the cascade. Now, the enzyme associated with it. Now, you can measure these by the ketone bodies in your urine sample or blood sample using the dipstick. This little strip you put in the urine sample, it tells you if you have ketone bodies or not, and so forth. So now it turns out when the ketone bodies form and it take it to different tissue, it has to be utilized, right? Your brains or muscles. So what happened, the acetate get clipped off to be attached first to CoA, but the CoA donor is acetyl-CoA. Now you have this acetyl-CoA. Now they get clipped to 2-acetyl-CoA. So this is in the target tissue after a ketone body is formed in your liver and taken to your target tissue, in your muscle cell, for instance, or your brain cell, you get clipped off and then later on get break down to the Krebs cycle. Is that clear? All right. So that's the utilization of your ketone bodies in your target tissues. Now, as I said, ketone bodies are acid. When the level goes up, basically when the utilization is lower than the output, so your blood pH starts dropping, right? Does that make sense? I'm sure you heard about ketoacidosis before, right? Diabetic ketoacidosis. So that's what happened. When you are in diabetic condition, so you have a lot of lipid mobilization, the fact that you don't have insulin, then your cells are sensing that the glucose is not being taken inside your cell. So even though you have a glucose in your blood, but the fact that the cells not having glucose being taken inside due to a lack of insulin cause the fat mobilization to occur. Does that make sense? Because the blood glucose is high, but fat cells not being able to take inside the glucose. So their sense inside as the glucose level, energy level is low. And that's the reason fat get released and they take it to different tissue for utilization. So once the ketone body level goes up because of high level of fat mobilization, and liver just take those fatty acids, break them down, and make ketone bodies and ship them to different tissue. Now all the tissues start utilizing them up to a point where they don't need it anymore. Then the ketone body is now sitting in your bloodstream. And the fact that they are acid, so the blood pHs are dropping. As you can see, the pKa value is 3.5, even though they are weak acid, but they are very much strong weak acid, if that can be said. Does that make sense? Okay. So the pKa value is very low compared to regular weak acid, so they can drop easily the blood pH. And what happened to pH drop in terms of hemoglobin transport of oxygen? So the hemoglobin will not be able to bind to oxygen, if you recall, right? The binding of the proton decreased the affinity for oxygen. So in your lung, your hemoglobin will not be able to bind to the oxygen, and that can affect the oxygen delivery. Is that clear? All right. I think that was the end. If you don't have any question, thank you. I know it's a lot of information, but if you have a question, I'll be happy to answer in your spare time.